In recent years, there are many excited news come out from time to time. I think when people discover there's some detectable radiation from the neutron star, where that the night wave was polarized. That prediction by Heisenberg 19 years ago would appear have been experimentally confirmed around 2007. You will check that publication. 2012 or 2011, I'm not sure. And there's, the big news. I've found the evidence for the Higgs particle. We know that the Higgs particle is a theoretical necessity for the Standard Model. The Standard Model was proposed in the 50s or 60s, around the 60s, that people are looking for a unified theory, which would ideally covers all particles, charged or neutral, mass or massless particles, so that people hopefully can explain every particles and their behaviors within the same framework called the Standard Model. In doing so, people have to, first of all, overcome all the mathematical difficulties, because the singularities seems everywhere. If you're not careful, you have to easily be disappointed. That is why, at the beginning, as Weinberger recalls, that the development was a little bit discouraging, because unlike the relatively simple treatment in the quantum electrodynamics by Feynman and others, that when you're dealing with interaction like strong interaction between proton and neutron and proton and proton, and then you will encounter quite unexpected mathematical anomalies or singularities. Of course, this is beyond the capability of experimentalists. But on the other hand, there are always intelligent people who are ready to show the world that mathematics can help. So that's why the group theory, the theory of symmetry, the idea was introduced, similar to the modulus arithmetic in number theory. In early days of the algebra, people trying to find the analytical formula for polynomial from the linear, quadratic, go to the cubic, quartic, and quintic. But unfortunately, when people went to the quintic equations, people realized that in general, there is no analytical solution. But instead, they receive patterns, unexpected patterns. And these patterns also appears when we study numbers. For example, if you build a clock, if you have a clock with different time intervals, we call the modulus in number theory. No matter how many numbers you have, if you put these numbers in a clockwise way, step by step, you will always end up with one of numbers which make this clock, which is called the modulus. Okay, so in other words, all numbers, probably the whole integers, all natural numbers, for example, can be grouped as different elements, different type of elements. In other words, the elements who are in the same category is divisible by the particular number of that module, and there are multiples. For any modules, a module with any numbers, then we can accommodate an infinite number. So we can put the number in these modules so that we can say, hey, this module or this group of numbers is divisible by that particular numbers and their multiples. So this is the basic idea of the group theory. and also being used for the study of the numbers in pure mathematics. Now, in the 1960s, people actually attempted, they have made some progress. By 1960s, the number of so-called elementary particles is just increased exponentially, and especially with increase of the possible energy achieved by a variety of the accelerators. So it would appear that there's no end to find it's impossible to put these so-called elementary particles into a small basket like Mendeleev's periodic table. So you see, that is a little bit very disappointed period, because you see, by 1940s or even earlier, that people actually by 1935, all of the three elements that made of all atoms in the periodic table has been found. They are the negative charge electron, positive charge proton, and the electrically neutral neutrons. These three elements or these three particles can be used to build any atoms. I think people should celebrate at that stage, because that is what people expect for since Democritus. At the beginning, it's a little bit abstract, but by the time when Dalton put his idea around 1803, and the atom became the physical, something real, because we can virtually to build in his day. Dalton actually can tell people that how to build, say, water, gases, and other simple compounds by using these elementary particles called atoms, called Dalton's atom. Although at that time, physicists didn't know that there's any internal structures. On the other hand, Newton's mechanics has been further developed into more compact, more elegant mathematical formalism, like the formalism built by Lagrange and Hamilton. We know that Hamiltonian now widely used in quantum mechanics, which represent actually, Hamiltonian actually represent the total energy of system. By that time, that people, both physicists and mathematicians, had built up the models which would appear very elegant and compact. But on the other hand, our knowledge about Dalton's atoms remain obscure. So many people, many physicists were trying to help. So one of them is Michael Faraday. So Michael Faraday is considered as not as a hero in physics, but also the hero in chemistry, because due to his contribution, due to his experimental works, that people gradually realized the charged particle in the substance play a very important role in all chemical reactions. Faraday mistakenly labeled this charged particle as anions or cations to indicate that they are either positively charged or negatively charged. But unfortunately, because he failed to understand that by nature, the opposite charge attract, similar charge actually repel. If Faraday paid more attention to the Coulomb's observation and Coulomb's law, then he wouldn't probably to invent these pre-modern chemistry terminologies such as ions, cations, and oxidations, reductions. Okay. So these terminologies are non-physical. It's just empirical, just people trying to. Of course, in the meantime, we have to mention that development in studying of the thermal motion, heat in particular. You see, in early days, and the heat was treated as a mysterious material, like fluid, invisible fluid. Yes, like dark material today. and so that they have proper, quantity definition. They have proper unit called Canary. But of course, eventually, after the James Joule, and the people realize that the heat is nothing but equivalent to work done, mechanical work done. Okay, it's just a slightly different way. It's just a slightly different way for energy propagate or transfer from one object to another. Another concept is a temperature. Okay, the scale of temperature is quite arbitrary. Okay, if you read the history about the temperature scale, you will find that sometimes the temperature zero just mean is arbitrary. Of course, except for the degree of Celsius. So they choose ice point, three-phase coexistence, three-phase of water coexistence. That is 0 degree. But of course, eventually by studying the gas initiated by Boyle, Boyle was considered as a father of modern chemistry because he brings the idea, the physics method, to study the gas. Before him, people just randomly choose pressure and temperature and to do the alchemy. Okay, I must emphasize the pre-modern chemistry is actually alchemy. Okay? It takes some time before people to realize what heat is. The heat is not it's a motion. It's just a more sophisticated, complicated types of motion when billions and billions of the particle move randomly. So that's why we have to introduce what we call microscopic properties. Microscopic property for individual particle, individual atoms, individual molecules. That is microscopic properties. So we still describe the motion of individual particle when we, for example, when we talk about the temperature, we actually refer to the statistics, the average of the proper quantity, such as average value of the kinetic energy of the individual molecules. That's where the statistics has been seriously adopted to study the thermal motion. So eventually we have people established thermodynamics from first law to second law or to the third law, and we learn a lot. By the end of 19th century, almost everything in physics would appear has been done. I mean, at a fundamental level, people knew the mechanical motion from the star to the object to the steam engine, and to the combustion, to electricity, electromagnetism, which has been unified. This is very, remember, I first time used unified. So Maxwell was a person who actually unified the electromagnetism and used in his 4 equations. Of course, all of the 4 equations were developed by others, except the last one, where he had introduced the flux, time-dependent flux of electrical field, which would be also responsible for the formation of the magnetic field. So in that way, he predict the existence of electromagnetic wave, which is happened to be the night. So night happened to be part of that spectrum of called the electromagnetic wave. By 1900, that Max Planck first explained that with many reservation, and he finally decided that to change the fundamental idea about electromagnetic radiation. Instead of describe the radiation using the wave models, he used oscillators, and eventually it actually also gives the proper unit for this energy called quanta. So later on, people call this quanta as a photon. Photon is a very strange particle because photon has no mass. Of course, you can argue that we still can work out the effective mass of photon by Einstein's relativity. That was 5 years later. So it's very strange. This just photon is just the basic unit of radiation energy. So which is simply determined by the frequency, the product of the frequency and the constant. That was a breakthrough in understanding physics. And because since Max Planck, electromagnetic radiation must be sometimes treated as discrete spectra or discrete particles, rather. So without this assumption, you can hardly avoid what we call the violent catastrophe. Now, after Planck, then there's Einstein became the second person at the beginning of 20th century to how to ignite the branch of the ideas, at least the three of them. So he published a paper in 1905. The first noticeable is the most famous one is his theory on so-called special relativity. Now, relativity is nothing new. Since the time of Galileo, physicists know that the motion are relative. So if you people standing on the bus and his observation with the people standing on the bus stop are different, sometimes opposite, right? So therefore, what you see, what you measure, is depend on the frame you choose, where the observer did his observation. So relativity or relative motion was nothing new. But something new is that by that time, there is a strong experimental evidence that the speed of light is constant everywhere. Because of that, so Einstein probably was the first one to explicitly talk about the implication of these phenomena. So light speed is the fastest, and nothing can go faster than speed of light. Besides, you cannot aid the light speed as we do when we actually travel at a lower speed. So because of that, Einstein's idea about space as time have changed a lot of things. Not immediately, because many physicists were working on the issues, how to understand the smaller microscopic world where the atom happened to be devised. By definition, atom in Greek means something you cannot divide it, okay, according to his definition in Greek. But around that time, around the first 20 years of the 20th century, not only were atoms being smashed into subatomic components, and together many invisible strange radiation or strange ray, including X-ray, alpha radiation, gamma ray, or beta ray, appeared or observed. So many physicists were busy on these issues, not just at experimental level, but also at theoretical in theories. After discovering the nucleus in atom by Rutherford, Bohr was the first to propose a phenomenological formula to explain the experimentally observed discrete spectra of hydrogen atom. His idea is rather simple. If you want to explain the discrete absorption or emission spectrums, then one have prepared to have the proper discrete energy formula. That is objectives. Of course, he didn't start with treated energy. He started treating momentum. Bohr proposed that the angular momentum is quantized. So he's trying to incorporate Planck constant in his new theory about atoms. Bohr's formula can be quantitatively explain the observed hydrogen spectrum. Okay, so that is a step forward, although there is no fundamental explanation of why should Bohr introduce this quantized angular momentum. In the meantime, de Broglie introduced his matter wave. So long as there is a momentum of particle, and there will be associated matter wave, and so that the wavelength can be determined by analogy of the Max Planck's photon. Now, based on these wave ideas, Schrödinger has first proposed that perhaps we can use a wave function to describe this matter wave. For the free charged particles in the uniform space, and the wave is a plane wave, it is easy to describe. However, in the case of hydrogen atoms, the electron is confined to this very tiny orbital around the proton. So Schrödinger himself found it difficult, enormous amount of difficult to use his equation, even to explain the hydrogen absorption spectrum. In the meantime, Heisenberg also had come up with ideas that, again, it's in the realm of discrete formalism, because you want to build a proper model in physics, you must based on experimental observation. Now, in those days, that observation of discrete absorption and emission spectra is something every theoretician must take into account seriously. So unlike Schrödinger's, Heisenberg came out some ideas quite different. He mentioned that his elements of these variables can be organized into a similar pattern as people used in matrices or matrices. So hence his new theory is known as matrix mechanics. When Paul Dirac first heard of Heisenberg's matrix, his response was, not very excited. Dirac is a person who likes to link the new theoretical challenges with existing, well-established classical formalism, in particular, the Hamiltonian and Poisson bracket. Yes, it is from the Poisson bracket Dirac eventually worked out that the link between the classical mechanics and the new mechanics. Nowadays, we call it quantum mechanics, but in his days, it's just, the coexistence of the matrix mechanics and Schrödinger's wave mechanics. So Dirac was the first person to realize that there is a mathematical similarity. The only thing he has to do is just to incorporate the H, the Planck constant, into that Poisson bracket. Now, how to do that? He just picked up the two basic quantities when describing the motion of the particle. One is the coordinate, another is the linear momentum. Okay. So these two quantities were used as a basis in the Hamiltonian mechanics formalism, so that people actually can treat this as a variable. But in classical physics, both variables are treated as continuous. The values for coordinate, the value for the momentum is continuous. Now, how do we recreate the Poisson-like bracket to incorporate new mechanics into the similar formula of the Hamiltonian or Hamiltonian mechanics? So that is the key. Do you know how did Dirac get that answer? He simply started the calculus, the first derivative of X and X himself, he worked out that commutative relation of these two quantities by carefully compare the nature or the consequence of what we call the product rule. You see the product rule? When you start calculus, you can either, if you have two operations, if you apply two operations on the functions, the order of this operation matters. Okay. For example, if you use the first derivative first and use the product, the x, then the answer will be different. So based on this fact, he built up his the most fundamental equation is called commutative relation between coordinate and the linear momentum from the product rule in calculus. So when you studied differentiation, or when you studied trying to work out the first derivative, you use product rule. So from the product rule, Dirac could work out these two very related quantities. So he called that, without hesitation, he called x is the coordinate. The first derivative of x is the determinant or dependent of the momentum. On the other hand, how to incorporate the Planck's constants? Dirac was the first person to introduce a complex number into the formalism. So therefore, you can see that in every textbook, the operator for momentum can be written as negative I h bar times first derivative or der of the der and der x. So that is how he built up this elegant and very compact foundation for the new mechanics. Eventually, we called it quantum mechanics. In Dirac's formalism, both Heisenberg's matrix mechanism and Schrödinger's wave function formalism can be considered as two different pictures. In Schrödinger's pictures, that the operator is time independent, while the wave function is time dependent, which is change direction of the length in the Hilbert space. In the Heisenberg's picture, where the wave function is fixed, time independent, whereas the operator is time dependent. So that is difference. So remember, if you go back to history, there's a heated debate between Heisenberg and Schrödinger, and they cannot convince each other. Okay, both think they are right, and both think other people are wrong. But it's quite unexpected. Dirac helped them to solve this seemingly unsolvable debate by using his modified Poisson bracket. Okay, that is a non-story. But another thing we have to mention to Dirac is that his contribution to combine his basic quantum mechanics with Einstein's special relativity. In those days, and I think also Schrödinger have done something, but he's not brave enough to publish his idea because that's according to recall by Dirac. Okay. So Dirac was the first person to start the electron because the electron is key to build the atomic model from the quantum mechanics. As you can see, that the simplest case would be the single electron in hydrogen atom, and then two electron in helium atom. Of course, by then we have to, when we started the jump from the single electron to the two electron, then you have to increase the complexity of wave function in order to take into account of the so-called not just Coulomb interaction, but also exchange interaction. Or by the way, that is where the idea of exchange interaction was introduced when you're dealing with the atom with more than one valence electron, like heliums. After Dirac had laid the foundation for the new mechanics known as quantum mechanics, his interest shifted to the electron, because in the early quantum mechanics, the electron was treated as a classical particle. In other words, the formula for the energy still uses the definition of in the classical mechanics, like the p squared divided by 2m plus the potential energy, because that is the energy we develop in the Hamiltonian mechanics formalism. Dirac trying to solve the problem. He tries to tell what would happen if we incorporate Einstein's special relativity, not general relativity, special relativity. And because after all, the gravity is weak compared with electromagnetic interaction. So therefore, Dirac was concerned what would happen if we use the energy formula from the Einstein's special relativity and to incorporate into the basic formula, or namely the equation of motion in quantum mechanics. So he's the first person to enter that area by combining the quantum mechanics and the special relativity. Well, the result was quite amazing, unexpected. He's not only theoretically predicted that there's a spin, each electron has a spin half. Yes, we use a spin. I used to study spin. I used to study electron spin resonance for 20 years. So that is spin, purely derived from that combination, from that marriage of the quantum mechanics and special relativity. In addition to that, we all know that he predicted the existence of course, what we call antimatters, anti-electrons, known as positrons. So that is quite amazing, just by merely combine the energy formula from Einstein's special relativity with the equation of motion in quantum mechanics. Of course, people, when we're looking back, they think, well, it's not a big deal. Perhaps some people might think, because after all, Dirac only dealing with simple just one electron. So still, in Dirac's theory on electron and radiation, still described by the classical electromagnetic field. So that is something people after him in the 40s, like Feynman and others, trying to extend Dirac's idea by quantize the electromagnetic field into photons, fundamental particles, with just for argument's sake. The field is called quantum electrodynamics. Basically, it's just dealing with a number of electrons and a number of photons. And when these particles interact with each other, the equation becomes so complicated, tedious. Still, they still use the very elegant notation introduced by Paul Dirac. It's called the Dirac bracket. It's bracket, if back to back, you got the two bracket, they have the dot product. And that formula is, even Dirac's bracket were used in the quantum electrodynamics. The equation is still too complicated, it's too long, too many terms, because you have dealing with a number of the particles, right? Now, Feynman was very clever. So he invented the graphic representation of these algebraic equations in quantum electrodynamics. So that is a famous Feynman diagrams. Feynman's diagram were not just used in dealing with electromagnetic interaction, but also has been extended to study other fundamental interactions, such as a strong interaction, weak interactions, not just a nuclear decay, beta positive decay, beta negative decay, and gamma decay, the annihilation of the positron and the electron, and the creation of this pair of electron and the positron from a photon. So these are just a few of the fundamental interactions that involved, which can be graphically explained by Feynman diagrams. But 1960s and 80s, and the study of the elementary particles, the heat has been decreased, you see. So you can feel that by 1980s, and the study in elementary physics is not as that popular anymore, well, meaning that the funding has been diverted into other study areas such as solid state physics, such as NMR and MRI. That was some of the attractive field of studies. So it's reasonably quiet to my knowledge. So, but there's something exciting happened in the mid of 1980s. That was the discovery of so-called high temperature superconductors. That was the first year I was in Monash University, where all of a sudden the department of the physics was polarized. Everybody is talking about a superconductor, doing experiment, they borrow some sample and to show some of the Mesler effect, and it's a little bit strange. You see, everybody were talking about superconductivity and what would happen if transition temperature reached to the room temperature. So at that time, I'm not very fan about superconductivity. So I just stay in my lab just to study the interaction between mycin and the DNA in the presence of the copper ions. I'm using electron spin resonance to study these combination structures, information, and so I was not interested in being involved with the popular science. Of course, eventually that heat wave eventually died down, and people could just return to their respective area of study. But there's for next 5-10 years, as a whole, it is quiet. And it is not until the report that the Higgs particle was experimentally observed in 1912, and all of a sudden, people in the field of particle physics are just became alive from the graveyard. They just return to the arenas that they just claim, oh yes, we got it, and we got that Higgs particle that is a mass donor that will solve the problem once for all within. Of course, they cannot talk about beyond interactions, that is electromagnetic interaction, the weak interaction, and the strong interactions. Of course, we have admitted that those mathematicians work in or theoretical physicists work in that area are very intelligent. Like they can, to introduce a finite number of the group or elements of groups, and to actually include all these particles observed, but also predict others. Apart from use group theories, so that they can reduce the necessary elements to the minimum. Now it's just a dozen of them. You can find this table in every textbook or website. Now this finite number of so-called elements include the 6 quarks and 6 leptons. They are the elements for matters, for materials, for the particles. And there are other particles, it's called boson. Boson is a quantized particle of interaction, which are responsible for the interaction between the matters, either the isolated quarks or their combined proton or neutron, and with other subatomic particles. I think that theory by itself is self-consistent. However, people are not satisfied. Some are just still not just dream, they just claim one day they can unify everything. even before the discovery of the Higgs particle. Many physicists have been trying to unify every interaction, namely the gravity. Gravity is very unique. Okay, gravity was the first fundamental interaction well studied by Isaac Newton. So apart from Newton's three laws of the mechanics, his law called universal gravitational law play a very important role. Still play a very significant role today when you launch the satellite, when you send the people to the Mars. You use Newton's mechanics. You use Newton's second law all the time. But for theoreticians and who always wish to, use some very sometimes called simple, but it's not simple theories to incorporate different interaction in the same framework. So that is called ground unified theory. I think also Einstein was one of the radicals to believe that his theory can solve all problems. Okay. Of course, his idea is not well accepted by people who work in the subatom or subatomic world, because they believe that those interactions, like the electromagnetism, like the strong and weak interaction, can never be described by Einstein's general relativity. So in essence, the basic idea of Einstein's general relativity is that they're trying to describe the physical stuff, like the gravity, in terms of the mathematical entities, such as geometry, to be specific, the curvatures of space or space-time, curvature of space-time, even more abstract. But this idea has been introduced in his special relativity, which is revolutionary and very fluid, just as I mentioned as Paul Dirac's theory on the electron, or Dirac equation, was built on both the quantum mechanics and Einstein's special relativity. But unlike a special relativity, in my opinion, Einstein's general relativity is a little bit beyond the approach physics has been used since Galileo and Newton and many others, like the Kelvins and Maxwell's. He's trying to rewrite everything fundamental in physics by taking into account of the space-time. And he said, well, if there is a curvature in the space-time, then there is you will experience a force, and where the light change direction. As I just recently shown that you don't have to. Without use the complicated general relativities, we still can derive by combined the Newton's universal gravitational law and Einstein's special relativity. We still can easily calculate the bend of the light wave by the sun. If you look at the recent development in both general relativity and the standard model, you will find that something in terms of timing is quite interesting. You see, the observation or the claim, what I call the claim of the existence of the Higgs particle, is few years earlier than the first observation of the gravitational wave, presumably originated from the merging of the binary black holes. This is quite remarkable, because all of a sudden, these two remote, extremely remote area in physics, all of a sudden got their breakthrough in terms of experimental observation. But I must make it clear that the observation of the gravitational wave implies that there's no gravitons people dreamed of from point of view of standard models. Do you know why? In Einstein's general relativities, there's no such thing called gravity, but simply the curved spacetime. So you don't need any exchange particles or like the gluons or the W or Z particles or photons there. You don't need that bosons. Okay, so to some extent, the Einstein's general relativity about gravity is something like magicians. You see, you just say, hey, here's this recipe, then you can create the force by just burn the space or by curve the space. Okay, who knows? My point is, although the key experiment observation in study of the gravity and the study of elementary particles occur almost at the same time, there's no indication that these two areas can be go together. In other words, in the case of gravity, as I mentioned before, if you accept that the origin of the gravity is due to geometry, the curvature of space-time, then you will be automatically excluded from the club of the standard model or the club of the ground unified theory of the universe.